Hello everyone. In this video we will see about an basic current mirror operation, and then we will perform this analysis and then transit analysis, and then we can see how can we find out the ratio of I out by I reference. Basically the current mirror is nothing but a copying of a reference current into the subcircuits. So whereas here we can observe here, this is the input current we are giving here. The same current will be get copied to the other end. So likewise we can copy the same reference current to many output currents. We can copy the same reference current to many subcircuits. So that is called current steering circuits. So basically the current mirror can be used to copy the same input current to other end. So this is the basic simple current mirror. So at first I have given VDD source with an resistance, and here we have short circuited the both drain terminal and gate terminal. So by doing so, the M1 will be always in the saturation region. So this will be VGS is equal to VDS. When VGS is equal to VDS, it will be in saturation region. The same VGS is applied to the M2 transistor. So by default, the M2 also will be in the saturation. So the same current will be copied to the I out end. So this is the basic current mirror operation. At first, we will see how to perform DC analysis. So to perform DC analysis, keep your voltage source as nil, nothing, and then give OK. Go to simulate, go to edit simulation command, and then give DC sweep and select your voltage source. Which source you are going to get sweep? So here the source name is V1, so please give the same name as a V1, and then the type of sweep we are going to perform is linear, and start value is 0 and end value is 10 voltage, and I'm going to increment by means of 0.1. So you can see here this has been enabled, this analysis has been enabled. So now let us perform a run. So right click over here and then add trace, and please select ID of M1 and ID of M2. So here we can see ID of M1 is black and ID of M2 is blue. The ID of M1 is called I reference current, and ID of M2 is called an output current. Both are same. The same current has been copied to the other end. You can see here this black same current, and ID of M1 and M2 both are same. That means that what we can infer from the graph is both we have kept the WL ratio for your both MOSFET as same. NMOS 1 also have the WL ratio of 10 by 5, and then the NMOS 2 also have the WL ratio of 10 by 5. So we people know that the current mirror's output current I out I by I reference is equal to WL of 2 by WL of 1. So here since we have both same WL ratio, the output is 1. We are getting same current. So now let us change the width of your MOSFET to 20 micrometer. Now let us execute the same circuit. Let us see what is the difference we can observe over there. So now once again go and add trace and give an ID of M1 and ID of M2. Sorry, I didn't change on the MOSFET. So go and change here. So please give 20, and then let us see what is the change. So here we can observe a change over here. Since we have the equation of current mirror is I out by I ref is equal to WL of 2 by WL of 1. So where here WL of 2 is 20 by 10. We have set at say 20 by 10, and then WL of 1 is nothing but 10 by 5. So we can observe a change. The ID of M1 is different from the ID of M2. So the current mirror operation, the output depends on the transistor sizing of your transistor. So this is the basic DC analysis. And then suppose for example, this is a normal DC analysis table. In this table we have as make an assumption that the channel length is 0, and then WL of 2 is equal twice of the WL of 1. That means that we have kept the n mass 2 as a 20 by 5 and then n mass 1 as a 10 by 5. So if it's so, what is the corresponding output currents? What is the I reference current, I in I out current? So we should make an observation, and then we can compare the simulation results and calculation results. So now to measure the corresponding output current when VDD is equal to 2 volts, when VDD is equal to 3 volts, and when VDD is equal to 4 volts. So how can we measure? So here in place of time you can give these are spice net list. So how can you add the spice net list? Means go to .op and then here you can add it up here. So that's how I have added up. So now I'm going to edit over here. We can measure it over here. So here in place of time I'm going to give as V1 is equal to 3 volts. V1 is equal to 3 volts. So we are going to find measure. The .mes means nothing but measure, and then which output node we want to measure. I have given as a IREF as an input node. So find is a keyword, and then ID of M1 when V1 is equal to 3 volts. This is syntax. So now let us execute. So once again we have already we have done that. So once again I will do it. So execute. So and then go on add traces of an ID of M1 and ID of M2. So here then go to view and go to spice error log. So here we can see here the at 3 volts what is the current ID of M2, and at 3 volts what is the IREF current. So and then the ratio is nothing but already the current the equation is I out by IREF. So the I out is 7.22 into 10 power minus 6 by 3.61 into 10 power minus 6, and the output is 2. Okay, since we have made a W ratio of twice of the input in MOSFET. This is a DC analysis. So now let us perform transient analysis. For transient analysis, keep an V1 source as a 5 volts constant, and then go to simulate and edit simulation command. Go to transient analysis. So I want to execute for 10 milliseconds. So I want to start from 0, and the maximum time step is I can go for 0.1 m. So here we can observe over here. So now go to simulate. Sorry, before doing that, we should see for transient analysis, we should find the output current when time is equal to 2 milliseconds and time is equal to 3 milliseconds, time is equal to 4 milliseconds. So now what can we do here? We can make a change in this equation when time is equal to 3 milliseconds. When time is equal to 3 milliseconds. So now once again go here, add trace and make ID of M1 and ID of M2. Click OK. So now we can find here what is the ID of M1. The ID of M1 is around 7.2 microamps, and ID of M2 is something like 14.7 microamps. Since we have a different WPL ratio, if both are same, then we can observe that both are same currents. Go to view and then go to spice error log. You should select your circuit diagram and then go to view, go to spice error log. for that. Yeah, now let us do for transit analysis. Run add trace id of m1 and id of m2. So now go to view Ltspice error log. So now you can see here at time is called 3 milliseconds. What is the ID current? At time is called 3 milliseconds. What is the input current? So IR by IR is 2. So since we have kept our WL ratio twice of the input transistor, so that's why the output is around 2. If you keep same ratio, then it will be same current. It will be 1. So then you can ask me a question that how can we add this model? So always the model is nothing but we are going to write a model for an is NMOS1. So NMOS1 name is given and then NMOS is there for which MOSFET. NMOS is the syntax and VT0 is threshold voltage. So we have kept the threshold voltage as 0.7 volts. W by L ratio and lambda. Lambda is nothing but channel length modulation and where KP is nothing but your mu in C ox. So we have kept as 10 micro and gamma is nothing but an bulk threshold voltage. So we have kept as a 0. So how you can ask me a question that how can we add this one? So always to add a new model or new directive, go over here and then you can type over here dot model nmos1 nmos, open the bracket, threshold voltage, width, length, lambda, and then your kp and gamma, and give OK means it will be get added up over here. Since I have already added up, I didn't add over here. So this is how you can perform a transit analysis and DC analysis for the basic simple current mirror. Thank you for watching.